So let's take a look at something that we call the Doppler effect. I found this picture on the internet. It's a pretty good explanation in case you don't already know what it is. So the Doppler effect is a physical phenomenon that occurs to any object that emits a wave. So object emits a wave. Now, this can be really anything as long as it's emitting some kind of wave, a sound wave, radio wave, a microwave, light wave, anything. And I'm not going to get into like the nitty-gritty details of what a wave is, but I assume you know that much already. So let's say that this is our object right here, and it's traveling in this direction, motion of source. Now it's emitting a wave, and normally if it was just stationary, the wave would be the exact same no matter where you were in relation to the object. But since it's moving in this direction, the same number of waves are compressed into a smaller distance, and this is on the side in the direction where it's moving. So think about it, it's kind of getting sandwiched between the direction that it's moving. It's like because as it's moving forward, there's another force, not really force, but you can think of it as like another force kind of pushing back on it like this, which compresses the waves. That's not really what it is, but you can think of it like that. And on this side, it's as if it's being stretched out because it's just dragging along. The waves are kind of dragging along. So basically, all you really need to know is that on the side of the object that it's traveling towards, the waves are going to get compressed. On the side of the object that it's traveling away from, they're going to get stretched out. So that is the Doppler effect. So next, we're going to look at this galaxy right here. So this is a galaxy called UGC 807, and that's the little picture of it right there. UGC 807 is in a random part of the universe. It's pretty far away, hence the bad quality picture. And I found this using what's called the Sloan Digital Sky Survey. This is basically just it's a tool. It's a utility free for anybody to use on the internet. That just has data of hundreds of thousands of different galaxies and stars in all corners of the night sky, and this is just one of the many, many. And today we're going to be looking at this galaxy. So basically, this galaxy is observing what we're going to call redshift. So let's change up the color here. Redshift. It's red now. So, how does this have to relate to the Doppler effect? Well, the universe is expanding, to put it simply enough. The universe is expanding, things are moving further away from each other, including this galaxy. This galaxy is actually accelerating away from us, very, very high speeds. So, this is us, this is the galaxy, and the galaxy is traveling away from us, and we're here. And the distance is increasing between us and the galaxy every single day. And this galaxy, the reason we can see it is because it's emitting light. So, actually, let me change the color, and you'll see why in a sec. There we go. So this galaxy is emitting light. So let's say this green wave thing, light. So this is starting to look familiar now. This is an object, it's emitting light waves, and we're receiving the light waves, but it's moving away from us. So since it's moving away, it's going to experience the Doppler effect. And that's where we get the term redshift. So you might see this wave. It's a pretty badly drawn wave. Let me actually redraw this. So let's say the wave looks something like this. So that's somewhat of a constant wavelength. And all waves have a wavelength, and this determines exactly what kind of wave it is. So since it's traveling away from us, we know the waves are going to get longer. This is a much longer wave. So the red one is what we're actually seeing, and the green one is what we should be seeing if the Doppler effect didn't exist. So see how the wavelength is actually increases a good amount between these two peaks. And this isn't really like to scale of how much of it's actually increasing. And this is on an extremely tiny scale. The waves are not nearly this large in real life. But basically, so the galaxy is emitting one kind of light, And actually, well, let me just show you something right now. So this is a spectrograph, what we call a spectrograph. So the spectrograph, basically, it takes in all the light that's coming, all the visible light that's coming out of the galaxy, and the x-axis represents wavelength in angstroms, which is 1 × 10 to the negative 10th meters, very, very small, 1/10 billionth of a meter, and this is flux, or light intensity. So basically, there will always be some amount of light on each wavelength. It just depends really on how intense that part of the spectrum is when we receive the light. So, for example, at a wavelength of 4,000 angstroms, the intensity is quite low, right around there. But we have all the way up to 7,000 or so, and the intensity is way high up. So these are the most prominent parts of the spectrum, as are emitted from this galaxy. So the different lines on the spectrum, the different parts of the spectrum, the different wavelengths represent different elements, or different spectra of light being emitted from different elements. So for example, you see this is the Na, that's sodium, that's magnesium. This is helium, but there's a bunch of hydrogens. There's hydrogen alpha, hydrogen beta, hydrogen gamma, hydrogen theta, or sigma, I don't even know, and neon, calcium. So all of these, each and every one of these, are actually representing the intensity of the light being emitted from these particular elements in that galaxy. And we notice immediately that the highest flux is coming from the hydrogen alpha light. So, and this is actually common because hydrogen is the most common element in the universe, and the hydrogen alpha light is typically the most common coming from stars and galaxies and such. So we notice that the hydrogen alpha has an intensity of very, very high up, around 40 flux, which flux around 40, but that's not really what's important to us as much as the wavelength. So we notice, if we draw a line down to here, sort of, the wavelength is about, let's say, 6,800, 6,850 angstroms. So that is the wavelength of the hydrogen alpha light. And this is the wavelength that we observe from the galaxy, the light that we're collecting from this galaxy, this particular galaxy, UGC 807. So UGC 807 is emitting hydrogen alpha light on this particular wavelength. So I've gone pretty far through this video, and I still haven't really explained what redshift is, and that's what my project is about. So I'm going to explain it to you guys right now. So let's just get rid of all this. So redshift. The concept of redshift is pretty simple. So let me put back the 6,850 because that's important. So we see that this emits 6,850, or the hydrogen alpha has 6,850 angstroms of wavelength. However, this is not the expected wavelength we'd get from hydrogen alpha. Hydrogen alpha actually is not quite on 6,850 angstroms. It's about 6,563 angstroms. So there's clearly a difference between these two values. So this is the one from the galaxy, and this is the one that we would expect to be coming from hydrogen alpha. Now, why is there this inconsistency between the two wavelengths? Well, we can explain it back to the Doppler effect. Because we have the galaxy moving away from us, like before, and now I'm going to be, let's say that that pink is the hydrogen alpha wavelength. It's going to get stretched out, right? It's going to get stretched out. And what does it mean when an object gets stretched out? Well, as we know from our lessons in this class, the period of the function is increasing. I mean, to put it in terms of sinusoid functions, and we can actually model this with a cosine function. So we're going to be modeling it with a cosine function. So here we have a graph of the light wave. So this is a theoretical graph of the light wave, but I'm sure it's a lot different for actual scientists who can actually measure this kind of thing. But for our intents and purposes, it's going to be one possible way to figure out a lot of things about this galaxy. So we're going to find the redshift. Now, the redshift is how far on the spectrum a particular light wave will shift to the right, or to the red part of the spectrum. So we're going to draw a fake little spectrum up here, and we're going to draw in the blue side, and the red side, because light spectrum, the ends of the light spectrum are visible light spectrum are blue and red. There's ultraviolet down there and infrared up here. So basically, what happens is when the wavelength gets stretched out, we're going to have a spectrum that is closer to the red side. Basically, it might even look a little bit red to us when we look up at it in the sky, because we start off with a spectrum of lines that looks like this, because this is a tool scientists use to because the way that we read what kind of elements are present in a spectrograph is using lines like these on the spectrum like this. So that the pink is what we expect to see. The yellow is what we actually see. So this is kind of a bad representation because I'm doing it by hand, but you should be able to see that the yellow is shifted towards the red side. And that's because red has a higher wavelength than blue. And when the Doppler effect stretches out the wavelength of the light, it's actually becoming a little bit more red. So that's where we get the name redshift. So the more you know, I guess. So let's get rid of this. So now that we know the concept of redshift, let's take a look at the graphs of the two kinds of light. So the black is what we expect to see from the hydrogen alpha, and this is actually accurate as far as wavelength goes. The x-axis is the wavelength, y-axis is the amplitude, I guess, which is just kind of the light intensity, but we don't have to worry about that for these purposes. But we're going to see that the wavelength of the black and the red part, well, the red is obviously the redshifted light, and the black is what we normally expect in a laboratory for hydrogen alpha. So the black has a wavelength, whoops, wrong color, don't want to have it like that. The black has a wavelength, as I said before, of about 6,563 angstroms. That is the distance between the two peaks of these wavelengths, and we are modeling this with a cosine function, where basically we take 2 pi divided by 6,563 to find b. We're going to do cosine bx to change the period. So basically, the cosine of it, we're going to end up with a function that's similar to, one sec, sorry about that, just had to get actual values for this. So we have for the redshifted equation, we have this cosine 0.000095736x. So that represents the function of the graph of the function for the red graph, and for the other one, for the non-redshifted one, we have cosine of 0.000911725x. That's rounded, even though to an insanely high decimal place. So this tiny difference actually can account for a lot as far as redshift goes, but this is just a way we can model it with sinusoid graphs. So clearly the wavelength has a pretty large difference over time. As you can see, they get kind of separated. But yeah, so this is just a way to visualize it, I suppose. We're going to delve a little more into what we can do with redshift and the nitty-gritty scientific details of it. So this is my graph of symbolizing redshift to model it. And you can actually derive a lot from this graph. We're going to cover that in just a second. So from this graph, it becomes clear that there is obviously a huge difference in the wavelength of these light waves that should probably change things for the light that we see coming from the galaxy. But we can actually determine a lot from this, and we're going to be going over something called the z values. So when we talk about redshift, in general, we have a variable called z, or more of a constant called z. And this is the equation that relates it to redshift. So z plus 1 equals wavelength of the emitted light divided by the wavelength of, or no, sorry. Okay, I'm completely getting this wrong. Wavelength of the observed light divided by the wavelength of the emitted light. I'm sorry about that. So lambda. Lambda symbolizes wavelength if you don't know that. So basically, we're going to take the wavelength in angstroms of both of these values. We're going to divide them and then subtract 1, and that's how we're going to get our z value. So z equals, we're going to have, what was it? It was 6,850 wavelength of what we observe from the galaxy divided by 6,563 angstroms, which is what we is normally emitted by hydrogen alpha. And we're going to subtract 1, get rid of the 1 on both sides. So when we do that, we actually end up with, just looking through my notes here, a z value of approximately 0.04373. So z value, very important. It's how we can derive everything, every single little tiny detail. So, so this z value is going to allow us to do a number of things. So we're going to start off with, we're actually going to be finding the velocity and the distance from us of UGC 807. So now that we have the z value, there are a series of other equations that we can do. So equation for velocity, very, very simple. We have v for velocity equals cz. So c is the speed of light in a vacuum, of course. And z is the z value, obviously, which we have down there. So we're going to plug this stuff in. V, not z. Z, no, oh my, okay, sorry. V equals velocity equals, so the speed of light is just under 300,000 kilometers per second. So we have, to be more accurate, 299,790, I'm sorry, man, okay, 299,792.4458 kilometers per second. And that's very precise, but the more precise, the better. Times, this is terrible, I'm sorry, guys, times, we're going to multiply by 0.04373. And we come up, when we complete that operation, we come up with a velocity of about 13,109.9241 kilometers per second. And that's because z is completely just a scalar value. It's constant, it's unitless, it doesn't have any units or anything like that. So we keep the units kilometers per second. So that is our velocity of the galaxy. V equals this. Velocity of 13,109.92419 kilometers per second. And that is insanely fast. And that just goes to show how fast galaxies travel and how huge and incredibly crazy outer space is. So now that we have z and v, we're ready to find our very last distance, which is d. Letter d, which is equal to v velocity times h0. So let's talk a little bit about what this h0 is. So the actual value of h0, which is a constant, is about 67 kilometers per second per megaparsec. MPC for megaparsec. what does this mean? Well, first of all, h0 is the Hubble constant, devised by Edwin Hubble. This constant expresses itself as the rate of expansion of the entire universe. Well, not the entire universe, that's what I'm about to explain. So basically this weird unit notation actually means that, or not megaparsecs, every 10 megaparsecs. So basically what this means is that every 10 megaparsecs you travel from Earth, space is expanding at about 67 kilometers per second more. So think about it. We have kilometers per second already, which is our velocity right there. And megaparsec is a unit of distance. It's an incredibly large unit of distance. It's what we use to describe the distances of faraway galaxies. And megaparsec is an incredibly huge distance. So now that we know kilometers per second, those are going to cancel out, and it's going to leave us left with megaparsec, which is our distance. So this is why we're able to calculate the distance using the Hubble constant. And there's plenty of stuff you can talk about with this constant. It's incredibly interesting, and I'd highly suggest giving it a look. But we're just gonna calculate this right now really quickly. So D equals, I'm not gonna write that all out. V times 67. And by the way, the Hubble constant is increasing as time goes on and the universe gets even bigger. It's actually getting higher up. This rate of expansion is actually increasing over time. So this is the estimated value of the Hubble constant for right now, this relative era. So we multiply this out and we get a final value. D equals about 195.67 megaparsecs. Now this is the final answer to the problem that I have posed for us today. And just to recap a little, what we did, we looked at the graph of the spectrum of, remember this, the spectrum of hydrogen alpha, and just the entire spectrum in general of galaxy UGC 807. And we looked at this, and this is a graph of the data, that has been collected by scientists in this survey that I told you guys about, and we compared it to the wavelength of hydrogen alpha in this spectrograph, and compared it to what we would expect hydrogen alpha to look like. So we took a look at that, and we derived a z-value from it, and the z-value is going to tell us how much this object has been redshifted. And this is the object that tells us how much it has been redshifted. I don't know if I was clear about that. That value represents how much it has been redshifted, and we talked about what redshift is. We talked about how the Doppler effect works, and how that relates to redshift. And then from then on, it was pretty straight. Oh, we looked at there we go. We looked at this graph of the two light waves side by side. We compared them. We saw that the period of the redshifted light was larger than the period of the non-redshifted light, at least when you graph it as a cosine function. We looked at this and we came to the conclusion that it was being redshifted, and we found this z-value. And with this z-value, there's two incredibly simple equations. Equation to find velocity, which is v equals cz. C is the speed of light. We found velocity very easily, and once you have velocity, well, you can calculate distance because you know how fast things are traveling in the universe. And we have that formula as d equals h0 v. So there we go. That is how you find that is an explanation of redshift, how you find the velocity and the distance, and how you can model this all with mathematics. The beauty of mathematics and astronomy is how beautifully they work together, and how you can graph things like this or like this, and there are equations like this, and it just works together like a charm, and it's just, you can find so many things with just one little ray of light coming from a galaxy that is about 195.67 megaparsecs away from us. So thank you so much for listening to me talk about this for like a really long time. This is one of my passions, and I'm so happy I got to share it with you today. I hope I enlightened you. I hope I taught you a little bit about one of the many ways you can model real life situations in mathematics and how it interconnects with astronomy. Thanks so much again, and sources are coming right up, so see ya.